So we're getting ready to wrap up this last piece of the activity and shift on to a new one. And what I want us to do before we leave is to come up with a conjecture for this problem number 7, which is to say if G is a finite group of order n, and K is the order of one of its elements, then what, if anything, can we say about K? So let me first talk to the diamonds group here real quick, just to get how you filled in these blanks. So the multiplicative group U8, first of all, what's the order of that group? 4. There's 4 elements of, there's 4 residues mod 8 which have multiplicative inverses. What was the order of the element 1? 1, because how many times do you have to multiply 1 by itself to get the identity? Just a single copy of 1 is all it takes, 1 to the first power. What about 5? What was the order of 5? Because 5 times 5 is 25, which mod 8 is equivalent to 1, the identity element. Right, so the order of 5 was 2. All right, how about in the additive group mod 8? What was the order of that group? 8. There are 8 residues mod 8 that have an additive inverse. So notice the big difference between A and B here. We're talking about multiplication as being the operation here, addition being the operation here. By the way, sometimes I'll make that explicit when I write these out, but sometimes, like here, I don't. So when I say U8, we're going to understand that multiplication is the operation. When I say Z8, we'll understand that addition is the operation. What was the order of the element 1 in Z8? 8. So we had to add 1 to itself 8 times before we got back to the identity of Z8. What's the identity of Z8? 0. All right, what's the order of the element 4? 2. Add it to itself once. 4 plus 4 is 8. Mod 8 is 0. How about 6? 4. So we had to add 6 to itself 4 times. 6 plus 6 plus 6 plus 6 before we got back to the identity. What is the order of the identity element in any group? Yeah, we can see sort of a shadow of that here in part A. That's just because how many times do we have to multiply? What power do we have to raise the identity to before it becomes the identity? First power. It is itself the identity. Note that we're excluding the 0th power. Right? In the definition of the order of an element, the order of an element is always greater than or equal to 1. Otherwise, it wouldn't be a well-defined operation because every element raised to the 0 power is equal to the identity in any group. So I wanted to talk through this. Let me also check in real quickly with the Hartz group. You were asked to give at least one good reason why the additive group mod 6 is not the same as the dihedral group with a triangle. And before I get your answer, what is one thing about these two groups that is the same? They have the same order. Both of them are groups with 6 elements. Here in Z6, they're the additive residues 0, 1, 2, 3, 4, and 5, mod 6. In the dihedral group of the triangle, it's the symmetries of an equilateral triangle. I'll just list them out here, right? It's E, R, R squared, T, TR, and TR squared. So both of these groups have the same order. But as we appreciated, hopefully, in the previous group activity to this one, having the same order for two groups is guarantee of nothing, right? It's a necessary condition for the two groups to be the same, but it is not a sufficient condition for the two groups to be the same. So what is it about these two groups that separates them, that makes them not the same as one another? What were the case that you were making? What were your reasons, Hart's group? Which one's not abelian? Dihedral group. D3 is not abelian. And why is that important? Because Z6 is abelian. Yep. So the operation in Z6, addition mod 6, is commutative. The operation in D3, the concatenation of symmetries of a triangle, is not commutative. TR, for example, is not the same as RT. So there's one good reason. What's another? Which one? D3 is not cyclic. Which, by the way, how do you know it's not cyclic? Maybe I'll put pause on that question real quick. How do you know Z6 is cyclic? What's the generator for Z6?
For Z6 is 1.
Sure. So 1 is an example of a generator for a Z6. Why? If you add it to itself repeatedly, it will account for all of the residues mod 6, right? 4 is 1 plus 1 plus 1 plus 1, and so forth. That's actually something I'm asking you to think about on the first question of the next group activity. So there's two good reasons. What's a third?
So we found that in the dihedral group, all of all of the elements was either 2 or 3.
Or 1, I suppose, right?
Or I guess 1, yeah, for the identity.
Only elements of order 1, 2, 3. And
Yeah.
why is that different from Z6?
So Z6, we didn't do all of them, but we did find one element that had order 6.
Yeah, right.
Which would have been
So Z6 has an element of order 6. D3 does not. Right? And therefore, these two groups, yet again, cannot be the same group. Right? So there's 3 good reasons. But I wanted to talk through them in detail because hopefully we've got some evidence up here on the screen that can help us to complete this conjecture. So when we look at the order of the groups in question 3, and then the order of elements within those groups, and we look at the order of these groups and the order of elements that live within them, what pattern do you notice in order to make a conjecture? What's the relationship, if any, between the order of an element in a group and the order of the group? K divides n. So K must be a factor or a divisor of n. And that, at least, is so far supported by the evidence that we have up here, right? This group had order 4, its elements had orders of 1 and 2. Order 8, elements had orders of 8, 2, and 4. Order 6, orders were 1, 2, 3, and 6. Right? So it feels like this is a reasonable conclusion, right? So far based on the evidence. Can we prove it? That's going to take us a little bit longer.